and started collaborating with Mauro Werder at ETH. And I was using Mauro's model GLADS, and that is going to be a major part of what I'm talking to you about today. This is the Glacier Drainage System model. It's looking at Antarctic subglacial drainage. I've since continued using that model, having moved to the University of Waterloo as a faculty member here, and now my students are using the model as well. So, the main thing I'm wanting to talk to you about today actually isn't the intricacies of this model. It's primarily about some of the major findings that we found. So I'm mainly going to be showing some of the results we've had modeling around the Antarctic in various different catchments. However, before we get into all that, shall we do a little bit of subglacial hydrology 101? And this is mainly from the perspective of a modeler. And so what we like to do in modeling is divide things into nice, easy packets in order to try and assess them in physical reality. And in terms of subglacial hydrology, the way we do that is we look at inefficient and efficient systems. Now on the left here is an example of a distributed system. And what this means is if we're using the example of an alpine glacier, then you have water coming in the spring, it reaches the bed of the ice. It's reaching a very, very difficult area for that water to flow through. It's very constricted, and so that water spreads out into linked cavities, and because it's very difficult to flow through the environment, the water becomes high pressure. It can lift the ice up off the bed and allows very fast ice flow speed. Now, once you have enough water going through the system, coming in from the surface, you can start getting areas where the water can flow slightly more easily, and these are exacerbated in flow over time and become channels that are eroded into the upside of the ice. And eventually we have a channelized system, which tends to be a lot lower pressure than the distributed system, just because it's easier for water to flow through here and widen these channels out with viscous dissipation of heat. Because they're low pressure, they draw a lot of the water in from the distributed system, and as a result, slow the ice down. And so what this means is when you transition from a distributed to a channelized system, you tend to see a very strong control on ice dynamics. And it suggests that, at least in alpine and Greenlandic glaciers, that the hydrology is really important for ice dynamics. Okay, of course, we know that nature is never as simplified as this. We have a whole host of things going on at the bed of the ice sheet. These can be generally categorized into efficient and inefficient. You've got some examples over here, different sizes of channels. You can have water flowing through sediment, water flowing in sheets between the ice and the rock underneath, and probably a whole host of other things that we haven't really thought about so far. Now, the problem is when it comes to trying to replicate that in a model, we really don't have enough information. It's very likely that a lot of these systems are varying on small spatial scales. So you could have a patch of sediment here, a patch of rock here. And first of all, it'd be very difficult to try and numerically code that up in a model. But possibly more importantly, we really don't have enough data. And I don't think we ever will have enough data to be able to replicate that on the spatial scales that would be necessary. And this is especially the case when we're talking about catchment-wide hydrology models, which tend to have catchment nodes of maybe 100 meters up to a kilometer. So if we're talking about things changing on the scale of tens of meters, we're not going to be able to see that in the model. As a result, what we tend to do is stick with our nice divided efficient and inefficient systems, as I showed on the previous slide. Now, here's an example that I like about illustrating why it's really important to care about subglacial hydrology. This is an example from Specularity in Iceland. And so what's happened here is you've had a volcanic lake growing underneath the ice in Grimsbotn. This lake has drained out through the glacier. And on the right here, you can see ice velocity. And the redder colors are where we've got faster ice velocity. And this just gives a really nice example of how, as this water plume is moving from the subglacial lake through the basal hydrology system, it's pressurizing, spreading out, and allowing the ice to speed up. And we can see it much faster here on the right. So it's clearly a very important aspect. And when we're looking at the Antarctic, we know that there are areas that are flowing very rapidly, and we know that the ice sheet is very susceptible to future change. And so thinking about subglacial hydrology in this context seems to me a really important thing to do. Now, so far when I've been talking to you about inefficient and efficient drainage systems, I've really been thinking of our alpine and Greenlandic-like systems. So on the top, we've got a diagram here showing a whole host of different things that are going on in Greenland. We have firn aquifers that are storing water over multiple years. We've got superglacial lakes that are cracking through the ice to the bed. We have moulins taking water from surface rivers. And you can see that, I mean, the size of these features on Greenland, there's a huge amount of water being pumped to the bed there. And while we still have work to do in Greenland, where there is, relatively well-known processes going on here in terms of how that surface water is allowing the basal system to develop over time. The problem is, when we go to the Antarctic, it's very different. We don't have surface water that's reaching the bed. Everything that we're looking at in terms of subglacial hydrology is produced in situ between the rock and the ice. So that means we have a big question mark over what is going on here. And it's likely to be very different to the systems that we're more familiar with in Greenland and alpine glaciers. And so the major thing that I've been trying to do over the last few years is address this question mark to try and find out what are the similarities and differences between these systems. And I'm hoping that I'll be able to show you these pretty convincingly during this talk. Okay, so we have no surface water in the Antarctic, at least on the ice sheets themselves. So how do we get a hydrology system at the base of the Antarctic? And there's a bunch of different things going on. Some of the most important are the geothermal heat flux. So we've got this nice insulating cap of ice over the crust underneath, over the rock underneath, and that allows this geothermal heat flux that's coming through the crust to warm the ice up at the base of the Antarctic, much warmer than it is at the surface. Those surface cold waves you get during the winter aren't reaching the bed of the Antarctic. And so you then combine that with friction that you have from ice sliding over rock, and we've got water being produced in situ because of that frictional heat. And of course, now that I'm in Canada, I have to have my obligatory hockey photo. So this is Connor McDavid, fastest skater in the land. And the reason he is a fast skater is because of a layer, a very thin layer of water that's between his ice skate and the ice. And the way that works is that the pressure that he's putting on these tiny little ice blades is changing the pressure melting point. So this means that water can exist at temperatures that are below what we know as freezing, with 0 degrees. And exactly the same thing is happening in the Antarctic. Some areas we've got several kilometers of ice that are overlying the rock. And what happens there is that you can reduce the temperature at the bed to a couple of degrees below 0, and we still have liquid water. So you combine this together, geothermal heat, friction, and the pressure melting point, and we can come up with a nice Antarctic map of basal melt. Now this is, if you look at these numbers, you may become slightly credulous about how the drainage system can be so dynamic, because we've got a vast 10 millimeters a year being produced in situ in the Antarctic. Doesn't sound like very much water, it's about that much. However, the Antarctic is a pretty big place. The catchments we have that are flowing into the ocean are huge. And so even if you only have 10 millimeters of water, the amalgamated water that's making its way towards the coast gets to be pretty substantial. And it's because of that that we can have some pretty interesting things that are going on underneath the ice sheet. So there has been work done on Antarctic subglacial hydrology before. One of my favorite papers is by Anne LeBrock and co-authors, and what they have done is they've mapped subglacial drainage networks assuming hydraulic potential at overburden. So what this means is they're assuming that the water pressure is everywhere at the same weight of the ice, and that allows them to map the most likely routes of water flow from the interior to the margin and the grounding lines of the ice. Now what they've then done is compared these outlets, so you can see them in blue here. So this is the grounded ice. The water's coming out into areas of floating ice, which is shown in the dark grey. And you see these lines that are tracking along here. These are basal channels in the floating ice. And the direct connection between the outlet of subglacial drainage and the basal channels means that there's a very good chance that this subglacial water is growing channels under the basal ice, or the basal floating ice. And so what's happening here is you've got your relatively warm, relatively fresh water coming out from underneath the glacier, and it's rising up the underside of these ice shelves, entraining ocean water with it and allowing viscous dissipation of heat to grow these basal channels that are then advected along. So the lesson here is that the subglacial drainage is having fairly significant impact on the draft of ice shelf channels. Other work that's been done by Livingston and others, what they did was again apply the same hydraulic potential analysis to look at the whole of the Antarctic and see how these drainage pathways are flowing from the interior to the margin. Now the thing to be careful of here is, although this is looking like a channel, it's not necessarily a channel. This is just showing a route of likely water flow and where that water flow is likely to come out. And the other thing the study did was have a look at where we're likely to get amalgamation of water in basins at the base of the ice, and therefore where you would have subglacial lakes. So this is really interesting for comparing between this method and the model method that I'm going to be showing you shortly. Okay, so everything I've been showing you so far is essentially assuming steady state. So that means the system isn't necessarily changing very much. In Greenland and alpine glaciers, you have a lot of change because you've got this surface meltwater that's altering on a scale of hours to days to months. And so that's going to change your drainage system constantly. Now, of course, without that in the Antarctic, we tend to evolve towards a steady state. However, we do know that there is active change in the Antarctic. And the reason that we know that is primarily because of subglacial lake activity. So there's been several studies using satellite laser altimetry, which is bouncing off the surface of the ice, to show how that surface is changing over time. You can see here on the left, we've got surface changes that are rising and falling over a scale of several meters. And this has been interpreted as showing water accumulating in basins under the ice sheet, lifting the ice up above it, and as those lakes drain, the ice surface drops down again. And so from this we can tell regions where you have a lot of active lakes, and on the right hand side, anything you see with the blue dot is argued to be an active lake. And so these are tending to be focused in the faster flowing areas, towards the outlets, towards the grounding line of the Antarctic, and so are pretty important in terms of figuring out the dynamics. And that's even more the case when you look at studies like those from Lee Stearns over here. What they found for Bird Glacier was that when a couple of the lakes drained, they got a very rapid increase in the ice flow. So it appears that these lake drainage events are directly impacting the rate of ice flow downstream. And we also know that lakes can act in tandem. So sometimes when you have a lake that's draining upstream, all of that water is flowing downstream and then allowing lakes downstream to grow and drain in their own right. So these are very linked features across the catchment. So this makes it an even more interesting place to look at subglacial hydrology. So we've got a very different system to Greenland and alpine systems, but we have dynamics that we're aware of. Now, in the past few years, things in terms of data processing have improved pretty dramatically in terms of subglacial hydrology modeling. So with new data products, it's a lot more, or it makes us a lot more capable of applying pretty complex subglacial drainage models to the Antarctic. And primarily what I'm thinking of here are basal melt products. So this is from the ice sheet system model. This is data provided by Matthew Morgan. And you can see here the variation in melt rates across the Antarctic. So these updated melt maps are extremely important for figuring out subglacial hydrology. We also have basal velocity rates, which I haven't shown here. And then of course the beautiful bed machine maps. You can see this spectacular basal topography, all these really nice troughs coming out. Of course, troughs are particularly irritating to model because they're very deep, steep slopes, but despite that, it's much better to have them included than not. And so with their increased data, we're having a much better applicability of complex models. So the model that I use, the Glacier Drainage System model, is a coupled 2D finite element model. And so what this means is that we have a whole bunch of triangles, which you can see here. The distributed system flows across the triangles, and our channelized system flows along the triangle edges. And the really great thing about this model is that you have mass exchange between the triangles and the channels. And so what that means is that we can develop channels naturally. So we don't have to tell the model where we think the channels are. It just develops depending on how much water is flowing through the distributed system, the pressure gradients, and how much exchange there is with the channels. So we know that when we see channels in the model that they're forming because of physical processes rather than because we're telling them that they should be there. So that makes it really, really useful and applicable to areas like the Antarctic, where we really don't have a great idea about where channels are flowing otherwise. The other useful thing about a finite element model is the triangles themselves, in that you can refine them in areas you're particularly interested in. So for example, at the grounding line, you can reduce the edge lengths to 100 meters, say, or in lakes, if you're particularly interested in a certain series of lakes, you can reduce the triangles so that you can get as much information as possible from those areas. What we tend to do with this model is have much larger elements at the head of the catchment, so further inland, because that's where our topography is less sure, our basal melt rates are less sure, and so it's less of an interesting place to look. We're more concerned about what's happening towards the grounding line, so it doesn't really matter if our catchment elements are larger higher up in the basin. Okay, I've had a lot of questions over the years about how we deal with parameters in the model like GLADS. Now, if any of you are familiar with this model, you know there's several things that can be tuned. And a lot of people have said to me, well, you know, isn't it easy? Can't you just tune the parameters to make the model do whatever you want? And that would be amazing. My life would be so much easier if I could, in fact, do that. However, the reality is a little bit more complicated, and it is essentially determined by how easy or hard it is to get water to flow through this model. So some of the parameters that we can change to determine this are, for example, the distributed system conductivity. So that tells you how easy it is for water to flow through. And our cavity height and width also is telling us how big a space needs to be filled before that system gets pressurized. So it doesn't really matter which of these parameters you choose. If you make any one of them too big or too difficult for water to flow through, it's going to have the same effect. So for example, on the left-hand side here, we've got Aurora subglacial basin. And you'll see here down towards the grounding line, we've got very, very low pressures. This is all below 80% of ice overburden. And so what that means is it's too easy for the water to flow through the system. We know that this isn't correct, and so we throw that model out, and we have to do something with these parameters to constrict the system a little bit more. On the right-hand side, it's a lot more realistic looking. We have higher pressures down by the grounding line, and we have higher pressures up in the system here. And so we can say we're more happy with this model output. Now, ideally, I would have been able to show you a model output where we've made it too constricted and too hard for water flow to get through. But what happens in that case is that the model won't run. If you have too much pressure accumulation in the system, it'll just break. And so we know then if the model breaks that we don't have the parameters right either. So what this means in the end is that we actually have a very narrow range of parameters where we can get model outputs that are reasonable. And of course, for every setup that we run, we have a range of sensitivity tests that check out those parameters so that we know generally what the range of options are for that basin. So to date, we've run GLADS for more than 50% of the Antarctic. Anything you see here in green is already finished. These data are available if anybody's interested in seeing these for your own research. I'd be very happy to share them. The areas in blue are in progress. So these are ones that we're currently running and applying sensitivity tests to. And clearly the aim for us is to try and get the whole Antarctic. So eventually we'll have the whole system together and we'll be able to amalgamate our results to get a full analysis of what's happening in the basal areas of the Antarctic. So we're pretty pleased with the progress of that so far. Now, I've already mentioned constraining the parameters that we have to try and figure out the range of options in the model. We can do an even better job than that by applying geophysical data sets. So one of the best ways for us to figure out the best model outputs is to use specularity content data. Now, the theory behind this is that you have a radar. So in this case, it's stuck on the bottom of a helicopter. You can also stick a radar on the bottom of a plane. You fly it over your ice. It pings to the bottom and gives you the ice depth. But it also can give you information on what the basal roughness is. So on the left-hand side here, where you've got a really nice specular reflection, that means there's something very flat that the radar is bouncing off. And in the case of the Antarctic, it's very likely that that is going to be water. So when we see high specularity content in the radar, we can assume that there's distributed water layers that are bouncing the radar back to the helicopter. If you've got a lot of diffuse radiation, so this means that the radar signal is bouncing in all directions, that probably means you don't have water. Or it can mean that you have a channel. So this is where it gets a little bit complicated. In order to have a specularity content reflection from a channel, you'd have to be really lucky and hit it right at the exact point where you'd be able to get your reflection. So this is illustrated in work by Dusty Schroeder for Thwaites Glacier. You can see your high specularity content in the middle here. That's showing that there's a distributed system. However, it's not likely that your water is constrained to the middle here and doesn't go anywhere. And so the fact that we don't have high specularity towards the grounding line doesn't mean that the water has disappeared, but probably that it's channelized. So we can tell from specularity content where we've got distributed water, less so for channelized water at the moment. So we've applied this in Aurora Subglacial Basin. So this is feeding Totten Glacier, which is down here. We've got Vanderford Glacier up here. And this is based on radar lines that have been run by Ice Cap project, run out of UTIG. And they're based out of an Australian station here. And you can see almost in the background the radar lines as they're coming up from the station. Anywhere you see a point over here is where the specularity suggests there is likely to be water at the bed. And so what we do is we look at the modeled pressure and water depth that we have for different runs in GLADS and figure out which is the closest match. So this is our best match over here on the right. And we can see a really nice correlation between where we've got high specularity and high water pressure, even to some small points up in the top of the catchment, which is, I was really impressed with how well this actually worked. Now, when we look at water depth, it's a little bit different. We have good water depth in the middle, but when we get down to the front here, we're not seeing high specularity in areas that we're seeing high water depth. And the reason for that is likely channelization, just like I was explaining for Thwaites Glacier as well. Just to show you a little bit of how we approach this, here are some other model runs for this area. You can see instantly the high conductivity run and the uniform velocity run here can be thrown out because we have very little water accumulation in the interior. We've got nothing to match with our specularity content. So it's unlikely that these model runs are correct. Low conductivity, you've got a little bit overshooting your water pressure up in the top. Uniform basal melt, we have similar problems. So I should explain as well that whenever we run these models, we're using generally variable basal melt input and variable basal velocity from ISSM. But because we're interested in the controls of water on ice flow speed, we don't want to precondition the model to give us the answer that we want. And so in addition to running those variable systems, we run it with a uniform melt and a uniform velocity, just to check that we're seeing the same signals there. One interesting thing is that the basal melt, the uniform basal melt, actually does a pretty good job of matching with the specularity. So it's possible that the ISSM basal melt rates aren't quite high enough in the upper catchment. And so this is a way that we can use multiple models to try and tune the system a little bit better to be closer to reality. Okay, so we have reached the end of me talking about the model specifically, and now we get to the really exciting bit, which is looking at the results that we have out of these models. So we're going to start off with looking at channels, and I've picked 3 basins here. We've got Pine Island and Thwaites on the left. We have the Weddell Sea sector, and this is Foundation Ice Stream and Academy Glacier. And on the right, we've got Aurora Subglacial Basin with water feeding into Totten Glacier and Totten Ice Shelf. So the first thing to point out here is how long these channels are. They're really long. We're talking hundreds of kilometers. Now, the reason that this is exciting is because when you look at systems like Greenland, you tend to have your channels limited to more of the 40-kilometer range. And the reason for that is because the channels growing in those areas are being driven by surface meltwater inputs. So if we don't have surface meltwater input higher in the system in Greenland, you can't seed channels and grow them. However, because our channels in the Antarctic are driven by entirely in situ melt, we can grow these really, really long channels, and they're pretty stable. And the reason for that is because we don't have generally a lot of variability going on in the basal system, and so that these can just persist in pretty large configurations for very long periods of time. The other thing I want to draw your attention to is that the volumes of water that we're having come out of the system. So Thwaites Glacier, for example, here you've got about 40 cubic meters a second of water being pumped out into the ocean cavity. We've got 20 for foundation, and we've got about 25 for Totten. So this is pretty significant in terms of ocean circulation. I mean, a lot of the ocean circulation models aren't taking account of subglacial drainage, but this is a constant water input coming in at the grounding line and could have very significant impacts on circulation in the cavities. I started working on this with Dave Gwither at the University of Tasmania for Totten Glacier, and we have found that the impact of the subglacial drainage is really quite important for changing the circulation in this pretty unstable sector of the Antarctic. So I think in terms of Thwaites and Pine Island, it's probably a really good idea to take that into account in the ocean modelling as well. In terms of the channels, they have other differences with Greenland. So the reason the Greenland channels are so important is because they do lower the water pressure. They're having a direct impact on the ice velocity overhead, and so really, really key for altering the ice dynamics as we go through a melt season. We don't see the same effect with channels in the Antarctic. Again, we're here, Foundation Ice Stream Academy Glacier. You can see the channel in black. You'll see the pressure here is pretty much at overburden. We're almost exclusively overburden all the way along. And if you compare the water pressure with and without channels, the channels only cause drop of water pressure generally at about 0.5%. So they're really not having very much impact on the water pressure in the system. And the reason for that is again because they're steady state. For these channels to exist, you really have to have a very delicate balance between how much water is flowing through them and the closure rate of the ice above. The reason that we can get much lower pressures in Greenland is because those channels are constantly changing size depending on the amount of water flowing in. But if you've got a very static, uniform volume of water going through a channel, it can equilibrate, so it's very close to steady state and has pretty minimal impact on the pressure system. So that means, although we've got very, very long channels, which are fascinating in terms of where they take water to funnel it out to the ocean, they're not really having that much of an impact on ice dynamics. Continuing a little further downstream, we're pleased that with GLADS we're having similar results as Anne LeBrock had with her matching of ice shelf basal channels and the subglacial outputs. And so I've put up an example here from David Glacier. So this is David Glacier. We have several radar lines running over Drygalski ice tongue, which is an ice tongue flowing out from David Glacier. And we can see from these radar lines that we've got multiple channels here. So these are pretty significant features, a couple of 100 meters high, even by the time you get 60 kilometers downstream from the grounding line, which is up here. Now what we've done is we've used an inversion of RIMA to figure out what the basal topography is, the basal draft of Drygalski ice tongue. You can trace these channels back up to the grounding line, and they match perfectly with where our subglacial drainage output is. So it's likely this variable draft here in Drygalski is entirely down, well not entirely, but primarily down to the subglacial drainage coming over the grounding line. We see similar results for Totten, Foundation Ice Stream, Institute Ice Stream as well. So we know that the drainage is coming out from the model in the right place. And so yet again, the subglacial discharge into the ocean appears to be having pretty big effect on the ice draft. An even more compelling argument for that can be made when you start looking at the melt rates of these ice shelves. So in this case, we have melt rates for Getz ice shelf and George VI ice shelf over here. Now these melt rates are produced using a mass conservation approach. And what we did was we plotted them independently of the drainage system coming out from GLADS. So what I'm trying to say here is that there was no tuning involved in this. We plotted them up together and you had an absolutely spectacular matchup between the outlet of these subglacial channels and areas of high melt. For example, down here, you've got the subglacial channel coming out here, and you can see this high melt region that tracks along the underside of Getz. We've got high melt regions here, where you've got a channel and another high melt region here. And on George VI, you've got similar patterns. We can see the high melt regions particularly focused around these channels here. And so clearly, the stability of these ice shelves in terms of their melt rates is being impacted by the subglacial drainage coming out. And so I don't think this is something we can ignore anymore in ocean circulation modeling. We really need to take account of this fresh water, especially since they're having such a significant melt effect. And we know that the thinner the ice shelves get, the more likely they are to break up, and that of course would be bad news for the grounded ice behind them. So definitely something to keep into account. Okay, so we've talked about channels, but moving on to the more distributed system, the high pressure regions that we find with GLADs tend to match up very, very well with our fast ice flow regions. Like I mentioned before, this would be a circular argument if we were telling GLADs what the melt rate and the velocity rate at the bed were in fast flowing regions, then of course you get high water pressure there. However, these examples I'm showing you are using the uniform basal velocity. So we're not telling GLADs where it's flowing quickly. However, despite that, you tend to get water accumulating at high pressure in regions of fast flow regardless. So just to confuse everybody, I've changed it up a little bit here. Instead of looking at water pressure as a percentage of overburden, we're looking at effective pressure. But all you really need to know is that where we have whiter, lighter areas and blue areas is where we've got particularly high pressure. So on the left, again, we have foundation ice stream, the Weddell Sea sector, and our high pressure areas tend to be focused pretty close to the grounding line up here. Now, if we look at our ice velocity map, we get pretty high velocities. This has been capped at 300, but it actually goes up a little bit higher than that. But you can see the regions of fast flow are also where we accumulate our rapid water, or sorry, our high pressure water. Now on the right-hand side here, we've got Recovery Glacier. This is, again, a little bit of a different plot. Because Recovery Glacier is a very dynamic region, it's got a lot of lakes, as outlined in black here. These are ISAT-defined lakes. That you have a pretty transient system moving through that glacier. And so instead of just plotting a snapshot of effective pressure, I've just taken the maximum effective pressure anytime. And because we've got lake drainage effects, these effective pressures are really quite low. I mean, this is pretty spectacularly low, actually. And so the dynamic impact of the water flowing through recovery is pretty significant. And we can see a match between our regions of high effective pressure and high velocity, down to even this small area here. You can see a sort of spike in velocity here and a spike in effective pressure here. So from this, it seems pretty convincing that the water is having a direct role on the ice flow speed. And so again, this should be taken into account, particularly because one of the biggest controls on subglacial hydrology is our ice surface slope. So as we start thinning our marginal ice, as ice shelves start weakening, we're going to be changing our slopes, and this will be changing with subglacial hydrology. So one of the aims we have in the future is to try and couple this to ice dynamics and figure out how the hydrology and ice dynamics are going to interact in a warming climate in future scenarios of the Antarctic. In terms of water pressure, it has other impacts as well as ice velocity. And the main impact is in terms of defining the catchments of different areas. So if we go back to the original way of looking at the hydrology system, which is taking overburden hydraulic potential. So once again, this is assuming the pressure is everywhere at overburden. In this example of Aurora subglacial basin, if you divide up the water flux between Totten Glacier down here and Vanderford Glacier up here, what you find is most of the water flows into Vanderford Glacier, not very much into Totten. Even if you drop the pressure everywhere below overburden to 90%, then still most of your water flows out of Vanderford Glacier and less out of Totten. Now, given that we know that Totten Glacier is far more dynamic than Vanderford Glacier, this doesn't make a lot of sense. You would expect more water to be flowing out of Totten. And indeed, when we apply GLADs, which is over on the left here, we find that the catchment is very stably divided towards more flux out of Totten and less flux out of Vanderford. This doesn't change particularly over time. It's always very consistently water flux into Totten. And so what that's telling us is that the variability of pressure, even if it is quite close to overburden, is driving the direction of water flow a lot more than you would realize when you're just looking at overburden hydraulic potential. So we know that the overburden potential is pretty good at predicting outlets of channels, but perhaps less good at figuring out what's happening in the interior. So I'd argue if you want to use hydrology models to look at interior fluxes, probably an approach like using GLADS or a similar model would be better than using overburden hydraulic potential. Okay, so everything I've told you so far is essentially, steady state systems. We're not thinking of much change over time. We're essentially looking at, pretty static channels, putting pretty static water output into the ocean. But right at the beginning of this talk, I mentioned that we know there are hundreds and hundreds of active lakes around the Antarctic. So this is something obviously of interest when we're trying to figure out dynamics. And we're looking into applying GLADS models in areas of active lakes. It is a bit difficult. It's not easy to get these things to model, but we have made some progress. But in general, I mean, there's some things that we can take away from the GLADS modeling of lakes. And I'll show you some specific examples in a minute. But the first thing is that we tend not to have a system like filling up a bath. So you can imagine you've got a basin underneath the Antarctic. You start filling it with water. At some point, that water gets thick enough to lift the ice above it, and that water can flow out the bottom. This is sometimes the case for lakes that are trapped in basins, particularly Jokulips in Iceland. And so it's not an incorrect model in those areas, but in the Antarctic, given that we only have, 10 millimeters of water in every position, it's a little bit difficult to imagine this volume of water filling up an entire basin. This 400 meters is just an example. You can have these over deepenings more than 1 kilometer deep, so that would be a huge amount of water. And so instead, what we tend to have is a system that's driven entirely by changes in pressure. So we start off with water coming into a basin. Now, one important thing to note is that at no point does water stop leaving the basin. We don't ever block water in the basin entirely. So you always have at least a trickle of water coming out the other side. What this means is because you've got more water coming in than going out, you start building a lake, and that lake begins to increase in pressure because that water has nowhere to go. And so now what you're doing is you're changing the pressure gradient between the lip of your overdeepening and the basin of your lake. So we've got a slightly less steep pressure gradient between the two now, and you can start having more water coming out the lake. As the lake gets deeper, we increase the pressure, even more water can come out the lake. And again, we're changing our pressure gradient here, making it easier for water to flow. Eventually, you're going to get enough water going over the lip of that lake, or the lip of the overdeepening, to start to see small channels. This blue blob is a channel, just in case you didn't know. And so these can be very small. They don't have to be particularly significant, but they are big enough to slightly lower the pressure, very, very slightly, from the surrounding system. And because of that pressure lowering, they again pull more water out the lake, and eventually the channels get big enough to drain the lake entirely. And this means that all of the remaining water in the lake gets pumped downstream into the drainage system, and potentially a further lake downstream. So here we've got our water draining. However, once you've got rid of most of your lake water, you no longer have the pressure to drive that water up and over the overdeepening lip, and so your channels start to close. And eventually your channels disappear entirely and you start again from the beginning. So you start building up the pressure of your water in the lake. So this is what we're seeing from GLADS all around the Antarctic. Anytime we've got a lake, it has that relationship where it's entirely locally pressure driven. So again, the assumption of overburden pressure everywhere doesn't match with what the model is suggesting is happening, and the dynamics that we see in these lakes do imply that the drainage system is evolving in terms of pressure over time, particularly when we're looking at catchment drainages. So I'm going to play a video here, which hopefully will work. Again, I've shown you before, this is Recovery Glacier. We've got our ice-sat lakes in red here, and we've got effective pressure plotted. Anytime you see a black line is a channel, and just remember that effective pressure, when it gets towards the white and the blue areas, is where we have high pressure. So if we start playing the video, hopefully you'll see water pressure building up at the beginning of the ice stream. This starts flowing through the lakes as the lakes grow and drain. We have an extra system here that we don't see in ice-sat. We have a slight offset with our lake. We haven't matched the location of the ice-sat lake. You can see channels growing between these lake systems. Now, the main thing I want you to take away from this is that because of these channels growing, what we end up seeing is that the lake drainage rates up at the top of the domain, the top of the ice stream, become less large. So we can drain them more easily and faster than previously. And so what that means is that the hydrology connectivity at the bottom of the ice stream, or towards the grounding line down here, is affecting hydrology hundreds and hundreds of kilometers upstream. There's a huge connectivity in these systems that is essentially just determining these pressure gradients all the way along the drainage systems. And so we've got this fascinating effect of things that are happening close to the grounding line that can affect things that are happening in the upper stream area. And so this would be something really interesting to look at in the Greenland context as well. Do we have similar connectivity in Greenland? Is this something that's restricted to the Antarctic, or is this something that we're just not fully aware of in other glacial hydrology systems? Okay, so those are the primary results that we've had out of the model so far. And I just wanted to talk briefly about the areas that we're going to take the model in the future. So the hope is to couple the model with the ice sheet system model. We're in the process of doing that at the moment, and so that we can have ice dynamics and hydrology interacting together. Now, Samuel Cook has produced a really interesting paper where a similar process was done coupling GLADS to Elmer ice and an ocean plume model. And so you can get some really fascinating results in terms of looking at how the hydrology is impacting the ice flow speed, rather than using pressure as a proxy, directly seeing how that interacts with the ice. So this is something we're going to be doing over the next few years with ISSM. Another area that I'm going down is looking at paleo ice sheets. So as I mentioned right at the beginning, we really don't have enough information underneath the Antarctic to be able to tell different spatial variability in basal conditions. But if you look at paleo areas, we have this absolute wealth of data in terms of where water was flowing, what types of water features you have. I mean, here's an example over in the Laurentide ice sheet of eskers that have grown due to subglacial channels. And so there's opportunities here to test the model and see how well it can replicate basal systems, depending on the scale that you're applying it. Of course, we have the problem then that we don't really know what the ice surface is doing, so you can never have everything you want, but it'll certainly be a very interesting way to test the application of the model and how hydrology has developed underneath paleo ice sheets as well. Now, a model is only as good as the data that you put into it, and so I would like to advocate for as much data collection as possible to help our modeling efforts. And of course, the International Thwaites Glacier collaboration is a really great example of how everybody can come together to collect data such as these. I've been talking to some members of this group about how potentially we can put in instruments into the ocean, or how they'll put instruments in the ocean and compare it with the subglacial drainage. So if we know exactly where these channels are coming out and how much water we think they're coming out, we can compare it with the ocean measurements and see how well the model is doing. Here is just an example of Thwaites and Pine Island over on the right. Anybody listening from Thwaites Glacier Collaboration, if you want these model outputs, just let me know. Happy to share them. But it'll be very exciting to see the data coming out of this collaboration and see how it compares with the modeling. Another great source of data are these specularity content derived from radar. And here is a map provided by UTIG. This is a collaboration with many, many countries, as you can see down below. All the purple areas are areas that they've collected radar over the years. And since 2014, any of these areas can be processed for specularity content. So you can see, like down here, we've got our Aurora subglacial basin, which is great. But there are several areas that would be really, really useful to have more data in order to compare with the hydrology models. So I'd just like to advocate people to push forward for getting more radar data in the Antarctic. It would be very, very helpful to push the subglacial hydrology forward. The final piece of data collection that I'd like to advocate for is a bit of drilling. Of course, if you get direct access to the bed, you're going to have some pretty interesting data, and this is really one of the clearest ways we can tell whether we're getting the right information from these models. On the left, you'll see a picture from subglacial Lake Whillans collected by the Wizard project. So this is really exciting to see data coming from subglacial lake. On the right-hand side, you may say, well, that doesn't look like an Antarctic drill to me, and you would be correct. That is in fact my Yukon borehole drill, so maybe not big enough to get through the Antarctic, but we can get down 400 meters in the Yukon. And we're applying that there essentially to do the same thing, to test how the model is doing against in situ data collection. So drilling is a really excellent, although expensive method to try and gather these data together. Okay, so we have reached the end. I'm going to just summarize quite quickly the major outputs that we've found from modeling over the last 6 years, comparing Antarctic and Greenland. So we'll start off with our channels. We know that in the Antarctic, according to the models, we have channels that run for hundreds and hundreds of kilometers. And this can be compared with Greenland, which tends to have channels that are a bit shorter, that run for tens of kilometers. So there's quite a big difference there. The reason for this difference is primarily because in the Antarctic, the channels are close to steady state. They're not changing very much over time, and so that they can persist very close to overburden pressure and therefore not fluctuate in size particularly drastically. However, in Greenland, of course, with your superglacial meltwater input, your channels are growing and shrinking in size over the melt season, and so that limits the longevity of these channels and how far they can persist up glacier. So I've already mentioned this for the Antarctic. Channels don't reduce the pressure much below overburden in the Antarctic, but in Greenland, the channels are really important for ice dynamics. They're really, really key for reducing the water pressure in glaciated basins below overburden, and so have a direct impact on ice dynamics, whereas the channels in the Antarctic don't seem to have that kind of impact. We do have several similarities between the two systems. In both the Antarctic and Greenland, we know that high water pressure can be linked with fast ice flow. And so this is going to be important in the future as we see evolution of the drainage networks in Greenland and evolution of the surface slopes in the Antarctic, where these areas of fast ice flow are going to be in relation to our high water pressure. In the Antarctic, the modeling has demonstrated that we can have hydrological connections across hundreds of kilometers along the catchment. This is a really interesting thought process in terms of drivers of change in the future. If you've got changes happening at the grounding line, these can be propagated all the way up the hydrological system to the interior of the catchment. In terms of Greenland, I've put this as a similarity, although I don't actually know if that's the case. I think it's likely that we have hydrological connections across a catchment in Greenland. We don't really know yet. I think this is an area that we could look at a little bit more in the future, and I suspect it's something that's similar between the Antarctic and Greenland systems. And finally, possibly the most important result is that the subglacial outflow from the Antarctic is impacting the ice draft of floating ice. So since we're extremely concerned about the stability of floating ice in the Antarctic, being able to incorporate the subglacial drainage into ocean models seems to be a really good step forward to understand how the subglacial drainage is impacting ice shelves and how it's interacting with other ocean water. And we know similar impacts in Greenland, with subglacial outflow impacts calving rates and potential front stability of tidewater glaciers as well. Now, of course, this kind of work is never done on your own. I have a lot of collaborators from around the world, so I'd like to thank all these collaborators for some really exciting work that we've done over the past 6 years, and looking forward to lots more work in the future. And I will just finish by advertising next week's talk. So we have Camilla Anderson, who's from GAES, who's going to be talking to us about glaciers in Greenland. And with that, I would be happy to take any questions.
Thank you so much. That was an amazing talk. Thank you very much. Are there questions? So the way we've done that this before is if you just type yes or a question into the box, we'll unmute you and you can ask your question straight to Christine. Anybody with a question?
Matt has a question.
Yes, great talk, Christine. That was really covered a lot of material, and it's an impressive array of things that you and your group have been doing in recent years. I have one specific question regarding your interpretation of the radar specularity data. And you showed a comparison both with modeled water layer thickness and water pressure. And I can see how the specularity content informs kind of the morphological conditions of water at the bed, but what is your interpretation for a physical justification to relate water pressure to the specularity information?
Well, I think what we're seeing there is essentially conditions that can allow a really nice flat surface. So the way that I see this is that if you have water in cavities that's not particularly high pressure, that's not going to be able to lift the ice up and spread out as a nice flat reflective shape. So it's only in areas that we've got high pressure water at or above overburden, and we've got distributed water systems that can spread that water out. Because, you know, if our cavities are pretty small, then you're not going to be able to see that particularly easily with a radar. So you're really looking at areas that have quite a widespread flow of water across the bed. So I think that's why the pressure seems to be a better comparison with the specularity content than the water depth.
Okay, yeah, thank you. We've been doing some similar comparisons with the specularity data for Thwaites with our hydrology model, and we noticed great comparisons with water pressure, but not water thickness, and we've been scratching our heads. So it's interesting to see that you've come to a similar result and have a useful interpretation. So thank you.
Are there any further questions? There's some jokes coming on the chat there. Any further questions for Christine? Oh, is that Johnny?
Christine, thanks. That was great. I had a question about your active lakes, your simulation in that animation you showed us. And at least the upstream ones seem to be migrating along as they filled and drained. And I was wondering if there is an explanation for that difference with the observations, if it indeed is a difference. Perhaps the lakes are migrating and we just don't know about it. What's your perspective on that?
That's a really good question, actually. I mean, part of that is to do with the quality of basal topography that we had at the time of running that model. So this was pre-bed machine. So it would be interesting to do it again and see if we have that similar pressure wave. But what I didn't show you was the water thickness change. So in that case, the depth of water in the lakes is more constrained to where those lake locations are, pretty coincident with where the ice sat lakes are. But it seems to be that the water pressure itself, as that water is going into and out of the lakes, is going as a wave down the system rather than being restricted into the lakes themselves. So it's yet again another difference between the pressure and the water depth. And I guess it suggests, if that is the way that it works, that we have to treat them a little bit differently.
I see. Thanks very much.
Any further questions? I was interested to know whether you can use the lake levels at all to constrain the model. You were saying that they weren't doing what we all thought they had been doing before, so in terms of draining.
Well, yes, I think that would be a very good way of doing it. I mean, what I should have mentioned was that the ICESat changes are also on the scale of a few meters. So the data are agreeing between ICESat and GLADS in terms of that mechanism of lake drainage. It's a little bit different from your collapsing cauldrons in Iceland. So it was more the Iceland versus Antarctic comparison that I was looking at there. But yes, I mean, it's a really good way to try and tune the model. We haven't nailed it yet with lakes. We haven't quite got the system to work. GLADS loves to go into steady state. It really doesn't like having transient dynamics. And so it's an active work in progress. And part of the problem is that because of that connection I was talking about over hundreds of kilometers, it's really difficult to get a scenario that matches exactly what's happening right now. When we did some synthetic tests on this, the lake drainage rates and timing were different every single time. And so to be able to get the exact, you know, if you've got 8 lakes in recovery, trying to match the ice sat changes with every single lake is going to be very, very difficult and potentially impossible with this type of model.
Alison, I think you've got a question.
Yes, thank you. Thanks, Christine. That was a really wonderful talk. I really enjoyed it. Yeah, quick question. You say that subglacial channels under Antarctica are close to steady state and that they don't reduce the water pressure much below overburden. I'm assuming that you think those scenarios may change in the future as melt rates increase and the channels start to enlarge and become more like the situation we see in Greenland. Is that correct?
Oh, yeah, really good question. Actually, as soon as we start getting water going from the surface to the bed of the Antarctic, it's going to change everything. I mean, it would actually be a very interesting test to try and simulate what would happen. You know, we'd change the surface slope a little bit for future scenarios and start pumping water into the bed. I think you're right. It would probably be very similar to Greenland. But then, of course, you've got this very large catchment that's still feeding water into the system. So that's a really good idea. It's a really nice thought for trying to figure out how that's going to change in the future.
Yeah, lots of people have talked about the Greenlandification of Antarctica. So yeah, right. That's where I was coming from there. Thank you.
Anyone with the last question? Here's one from Matthew Hoffman saying, you touched on parameter calibration for the distributed system, but what have you done for tuning the channelized drainage? Are water flux magnitudes and locations across the grounding line sensitive to channel parameter calibration?
Oh, that is a good question. Yes, we do have abilities to tune the channels as well. And that is one of the sensitivity tests that we run for GLADS every single time we apply it. So we have a higher and a lower conductivity channel. And usually it's pretty static in terms of the outlet locations, but occasionally it changes. We do have a situation at Totten Glacier where you change the channel conductivity and it does shift the outlet location of that channel. And so that is where we can start using these basal channels in the ice shelves to determine where the subglacial water output is coming out. And similarly with the melt rates, when we got high melt rates right next to the grounding line, it's very likely that there is a channel coming out there. And so we can tune in that sense, but it is a little bit dangerous to use these type of data to both tune and analyze your outputs. Like you don't want to have everything as a circular scenario. So it is really encouraging that for quite a lot of the areas, so Getz, George VI, where else? Foundation ice stream, the channels really don't change despite changing the conductivity of them in terms of grounding line location anyway.
Does that answer your question, Matthew? Are you happy?
Yeah, no, that was great. And sorry if I cut anyone else off by asking a second question. Just very excited about the work.
There's a question from Helen Fricker. So she's got weak internet, so asking this on the chat. What data set are you using for ice sat volume changes?
Good question. I mean, primarily the ice sat volume changes have been applied to, I was looking at Recovery Glacier. So for that, I was working with Beachaco from University of Buffalo, and they were processing ice sat lake volumes there and providing me with those data. However, if you would like to provide me with more data, that would be great. I would like to have some updated volumes if you've got them. That would be really exciting. Okay, I don't see any more questions coming up unless I've missed anything. One from Bernd here. For the paleo ice sheet situation, could you invert the analysis and infer ice sheet surface height changes from, e.g., evidence of escalocations and changes in time? Yes, that's a really good idea. I think we've only just started thinking about how to apply this to the paleo situation. So there's going to be a lot of iterations of trying to figure out the best approach for this, but certainly using the esco locations is one of them. I think one of the issues is we don't really know how eskers are formed entirely at the moment or how rapidly they're formed. So in terms of the drainage, you'd probably be looking at just trying to match your channel locations with the eskers. The paleo ice sheet models surfaces tend to not have a lot of small scale variability. So there is also efforts we're talking about to try and use the basal variability to get a roughness parameter on the surface. There's been some work done on this in Greenland to figure out how the surface can look depending on different basal topography. And so we'll probably try something like that. But other than that, you know, how long is a piece of string? You could change the surface dramatically, and we wouldn't really know one way or the other. So I think this is going to be a bit of a challenge, but something we'll have to see how it works. And if anybody has any ideas about how to approach this, I'd be really happy to talk to them about it, because yeah, it's going to be fun.
Okay, thanks, Christine. I think we might have to have a bit of a chat about this. It's extremely interesting. Thank you.
Any last questions, or have we run out there? No. I think we've run out, and we've just got lots of thank yous on the chat. So thank you indeed for a fabulous talk. Yes, and thank you everyone for coming. It really feels like it's bringing the community together to see everyone in seminars like this. So thank you to everyone. You hit 100 and something in the middle of your talk there. So thank you very much indeed. So see